Hello everyone, let's analyze. So today we're going to talk a little bit more about improper integrals. So one application of improper integrals when we generalize to n-dimensional space is we can use an integral to give us the volume of a set in Rn. Now I say n-dimensional volume because volume means different things in different dimensions. For example, the n-dimensional volume in one dimension is length. So we see here that the volume of an interval is just the length of the interval. Two-dimensional volume is what we typically call area. Three-dimensional volume is what we typically call, well, volume. And four-dimensional volume is, well, perhaps a bit difficult to visualize, but once we have the machinery of multidimensional integration is something computable. Now, if A is not an interval, as in the previous example, then we'll use the same method as before, as just defining a function that's 1 in the domain and 0 otherwise, so that the integral over A is the same thing as the integral of this, what's called a characteristic function when it's tied to a set over the real line. Of course, I could replace the R in that integral with an interval if A is contained inside a closed interval. If the integral does not exist, then we say A has no volume. Now, it's important to note that A has no volume is not the same as saying A has volume 0. Those are different statements. A has volume 0 means that integral is equal to 0. We'll see an example of that in just a little bit. A has no volume means that integral doesn't exist. So for example, consider the set of all rational numbers between 0 and 1. Now, we've shown previously that the function that is 1 when x is rational and 0 when x is irrational, that integral does not exist. So in this case, we would say that this set has no volume. Now let's consider another example. Let's consider the set of every reciprocal of every natural number. So 1, half, a third, a quarter, a fifth, a sixth, and so on. So this set is contained in the closed interval 0 to 1. And the characteristic function is 1 if x is, well, a reciprocal of a natural number and 0 otherwise. So let's take a look at how we would measure the volume of this set. So here in this picture, the blue lines represent the characteristic function for our set, right? So notice these blue lines have a value of 1, we see up here, when x is a reciprocal of a natural number. So 1, half, a third, a fourth, a fifth, and so on. Now it should be clear that if we were to partition this interval from 0 to 1, the lower sum for every partition is going to be 0 because every interval is going to contain some number that's not a reciprocal of a natural number, no matter how we partition. So let Pm be a partition such that the first partition has a length of 1 over m. So for example, if m were 5, we would see the first two partition points there, 0 and 1 over 5. And let's let every subsequent partition be 1 over m squared. And now let's evaluate the upper sum for this partition. Again, we see an example below of such a partition if big M is 5. Well, for the first partition, of course, the supremum of f is 1. So we would get the rectangle with height 1 and width 1 over m plus, well, how many more subintervals will the supremum be 1? Well, at those 4. In fact, for any m, to the right of 1 over m is going to be the reciprocal of every number less than m. So we're adding to 1 over m the sum of rectangles whose height is 1 and whose width is 1 over m squared, and there's m minus 1 of them. Well, that's equal to 1 over m plus m minus 1 over m squared, because notice that what's being summed doesn't depend on k, so it's just 1 over m squared times however many there are, m minus 1. And that goes to 0 as m goes to infinity. It follows that, remember that the lower sum is always 0, so the supremum of a set containing just 0 is of course 0. The supremum of the lower sum is less than or equal to the infimum of the upper sum, right? That's one of the results from our section on integration. And that's less than or equal to the limit, because every term in that sequence indexed by m is in the set of upper sums for all partition. So whatever it converges to must be greater than a lower bound, and an infimum is a lower bound. And of course, the limit as m goes to infinity is 0. That's what we just proved. So if the lower integral, in other words, the supremum of lower sums, is 0, and the upper integral, that is the infimum of upper sums, is 0, then my integral is integrable, and the volume is equal to 0. So here we have an example of a set whose volume is 0. So the volume exists, but it's 0. So you've seen an example of a set that has no volume and a set that has 0 volume. And we saw how they're different things. So one of the most useful tools for evaluating and analyzing improper integrals is the comparison test. It essentially says that if, for example, the blue curve is integrable from a to infinity, then so is the red curve. Now it also says that if the red curve diverges, then the blue curve would also diverge. Of course, the requirements are that both the blue line and the red line are integrable over every finite interval, and that f is non-negative. Of course, g has to be non-negative in both scenarios, because in the first bullet, g is between 0 and f, and in the second bullet, g is greater than f, which is not negative. So let's prove it. Well, let's prove this first bullet. We'll leave the second bullet to the reader, but the idea is similar. Let SFB be the integral from a to b of f of x. In fact, SF is an antiderivative of f if f is continuous, for example, evaluated at capital B. Notice that this function is increasing with respect to b because f is positive, so as b increases, the area under the curve, which is always positive, is going to increase. Furthermore, in the first bullet, we're supposing that the integral from a to infinity of f converges. Well, the integral from a to infinity of f is just the limit as b goes to infinity, and that equals something. Let's call it L. Let's define a similar function for g. Right? Sg of b is the integral from a to b of g of x. Now, because g is less than or equal to f, the integral from a to b of g is less than or equal to the integral from a to b of f, which is equal to sf of b, which is always bounded above by L. We know it's bounded above by L because it's monotonically increasing and converges to L. So it never passes L, it only gets arbitrarily close to L, perhaps at some point equals L but never passes L. So it's always less than or equal to L. Now, since G is non-negative, SG of B is increasing and bounded above. Well, an increasing function that's bounded above converges as B goes to infinity. So let's call that limit L prime. L prime is some number less than or equal to L. And while the fact that that limit exists means that the integral from a to infinity converges. Furthermore, it's equal to the integral from a to big A of g of x, which by hypothesis is integrable, plus L prime. In other words, the integral from big A to infinity. And so we've proven the first bullet. And again, the second is similar. And I would encourage the viewer, the reader, the listener, to stop and consider how they might prove that second bullet. Another useful tool is the limit comparison test. If f and g are both Riemann integrable over any interval a to b for every b past a, and if the limit of the ratio of f to g is equal to L, which is non-negative, then if L is positive, the integral of f from a to infinity converges if and only if the integral of g from a to infinity converges. Now, if L is 0, we don't get an if and only if. We get that the integral of g converges, that if the integral of g converges from a to infinity, then the integral from a to infinity converges. And if L is infinity, then if g diverges integrated from a to infinity, so does the integral of f from a to infinity. So we have three different scenarios. So as before, we'll prove just the first bullet, and I'll leave the proof of the second two to the viewer. So suppose that the hypothesis is true. The limit as x goes to infinity of f divided by g is equal to L, and that the first bullet is true, or that the first phrase of the first bullet is true, that L is strictly greater than 0. Now notice this is an if and only if, so we have to prove two different directions. But first, let's just consider this scenario. What does it mean that the limit as x goes to infinity is equal to L? Well, it means there exists a point, big A, to the right of little a, so that if x is greater than or equal to big A, then the difference between my quotient and my limit is, well, as small as I would like, and in this case, I would like L over 2. Well, by the definition of the absolute value, that means that the difference between the quotient and L is between negative L over 2 and positive L over 2. And if I add L to both sides, it's between L over 2, which is positive, and less than 3L over 2. Notice this implies that if x is greater than or equal to big A, f divided by g is positive. So f divided by g and the absolute value of f divided by g is the same. Now, it could be that f and g are both positive. It could be that f and g are both negative, but their quotient is positive. So that means I can bound the absolute value of f by a scaling of the absolute value of g for every x past big A. Now we're going to prove the reverse direction. Suppose g converges in the integral from a to infinity. Well, that means necessarily that g plus and g minus converge. Right? In this scenario, we don't know whether g is a non-negative function or a non-negative function. Right? G is rather arbitrary apart from the hypothesis and the theorem. So if g converges, by definition, it means g plus converges and g minus converge in the integral from a to infinity. Now, because the absolute value of f is bounded by a scaling of the absolute value of g, that means f plus is bounded by 3L over 2 times g plus, and f minus is bounded by 3L over 2 times g minus. Remember, f plus and f minus, g plus and g minus, are both equal to the absolute value of the function, just with different domains. So, by the comparison test, since g plus and g minus converge, f plus and f minus both converge in the integral from a to infinity. So here we've used the comparison test. And since f plus and f minus both converge in the integral from a to infinity, then so does f. So we've proved the reverse direction. In fact, the forward direction is similar. So we have it there. It's the exact same idea. If I suppose f converges, f plus and f minus converge, g is bounded above by 1L over 2 times f, both g plus and g minus and f minus. So I can apply the comparison tests to get that g converges. So it's the exact same idea. The Bolzano-Koshi criterion. So let f be Riemann integrable from a to infinity. So this is an improper integral, but we're assuming that it's Riemann integrable over any closed interval a to b, where b is any number to the right of a. Then the improper integral converges if and only if, for all epsilon, there's a big T such that any interval to the right of big T has an integral whose absolute value is less than epsilon. This is essentially saying that if an improper integral converges over an unbounded domain, then if I go far enough to the right, the area under the curve in magnitude must be arbitrarily small. That's all that this is saying. So the next result we're going to discuss is the LeBlanc monotone convergence theorem. Let Gn be a sequence of non-negative functions so that each improper integral from 0 to 1 exists and is finite. Suppose that for every n, Gn is non-negative, and that the sequence is decreasing. In other words, Gn plus 1 of x is less than or equal to the previous function in the sequence, Gn of x. So we have a monotonically decreasing function. And that's true for all x in the interval 0 to 1. And suppose that this decreasing function converges to 0 pointwise for all x between 0 and 1. Then the limit as n goes to infinity of the integral Gn of x is 0. Now remember, we said that the integral from 0 to 1 of Gn of x exists. If I take the limit of those integrals indexed by n, I get 0, according to the LeBlanc monotone convergence theorem. So let's take a look at an example. Let's show that the limit as n goes to infinity from 0 to 1 of x to the p times e to the negative nx dx is 0 so long as p is greater than negative 1. And we're going to use the LeBlanc monotone convergence theorem, or the LMCT for those in the know. Now, note that as x approaches 0 from the right, because again, we're only looking at the interval between 0 and 1, my integrand is 0 if p is positive, 1 if p is 0, but infinite if p is less than 0. So that integral we're looking at is in fact an improper integral if p is less than 0. Now, what that implies is that if p is equal to 0 and greater than 0, then I have a continuous function that is bounded on a closed interval. So of course that integral exists. Now, e to the negative nx, right, that's 1 over e to the x raised to the nth power. And if x is between 0 and 1, e to the x is greater than 1. 1 over e to the x is less than 1. And if I raise that to the nth power, I still get something less than or equal to 1. Of course, equal to 1 is 0. Now, I also know that the integral from 0 to 1 of x to the p converges if p is greater than negative 1. So, if we apply the comparison test, the integral from 0 to 1 of x to the p times e to the negative nx dx converges so long as p is greater than negative 1. So, this integral is integrable for p greater than negative 1, for p equals to 0, and for p greater than 0. In other words, for all p greater than negative 1, this integral exists. Now, e to the negative x, for x between 0 and 1, as we just pointed out, that's less than or equal to 1. So then if I say the n plus first function is x to the p times e to the negative n plus 1 times x, that's less than or equal to x to the p times e to the negative nx, because the only difference between the left and the right is the multiplication of e to the negative x. And that's the nth function in my sequence of decreasing functions. Right? So again, we're showing that we're satisfying the hypothesis of the LeBlanc monotone convergence theorem. Right? We've shown that if p is greater than 1, this exists and is finite. We've shown the decreasing property. Now we need to show this property, that my functions converge to 0 pointwise. Okay, since we only need pointwise convergence, let's fix x. Let's x is equal to x naught. It's fixed, it's not moving. X naught is just some number between 0 and 1. And let's let n go to infinity. Well, the limit as n goes to infinity of gn of x naught is the limit as n goes to infinity of x naught to the p divided by e to the x naught to the n. E to the x naught is greater than or equal to 1. Raise it to the nth power, that goes to infinity. It's in the denominator. The numerator stays constant as n goes to infinity, so I get 0. So now I've shown that gn converges to 0 pointwise. Therefore, I can say that the result of the theorem is true. The limit as n goes to infinity from 0 to 1 of my function equals 0. Right, so here we've applied the LMCT by showing that our sequence of functions satisfy the hypothesis, and therefore the result is true. A corollary to the LMCT, let fn and f be non-negative integrable functions. Suppose that fn is increasing, in other words, 0 is less than or equal to fn of x, which is less than or equal to fn plus 1 of x. And that f, which is the limit of fn of x pointwise, exists as an improper integrable. Well, then in that case, the limit as n goes to infinity of the integral equals the integral of f. So let's prove this. Well, it's a straightforward application of the LMCT because I just take the difference between f and fn. Because fn is increasing, the difference between the limit and fn is decreasing. And of course that difference converges to 0 pointwise because fn converges to f pointwise. So by just applying the LeBlanc monotone convergence theorem, we get that the difference when integrated from 0 to 1 converges to 0 as n goes to infinity. We can expand that integral and we get the result that we're seeking. So let's take a look at an example. Now that we've proved the corollary, let's apply it. Let Gn be non-negative. And let g of x equal the series of functions gn of x. So we're supposing that, in fact, that equality is valid. In other words, for each x, the series gn of x is equal to a number. So we get, at the very least, a pointwise convergence. So we're going to suppose that's true, and that the integral from 0 to 1 of g exists. Right, so we're trying to essentially use our machinery to say, what does this tell us about series? Because, of course, a series is nothing more than a sequence of partial sums. So our task is to show that the integral from 0 to 1 of g, the pointwise limit of my series, equals the sum of the integrals of gn of x. In other words, that this summation can be distributed. So let Sn be the partial sums. Since gn of x is non-negative, my partial sums are increasing, and they're converging to g. So by the corollary, the limit as n goes to infinity of my partial sums equals the sum of my integrals of gn, which is the integral from 0 to 1 of g of x dx. So let's take a look at yet another corollary, which says that if a maps the interval a to b to r and f is non-negative, and the improper integral from a to b of f squared exists, then the limit as m goes to infinity of the difference between f and fm squared goes to 0. Now remember what fm is from our previous lecture. Fm is just f if f is less than or equal to m and 0 otherwise. Well, if I just consider the difference f minus fm squared, as m increases, fm gets closer and closer to my actual function. Right? I'm capturing more and more of the function. Therefore, the difference between f and fm satisfies the hypothesis directly of the LeBlanc monotone convergence theorem. And that gives us our result. Well, that's it for today.